move to the second part of chapter 31, and that is gonna appear as just chapter 31b. Now we are going to study component by component and how really when the AC current, which is the alternating current, is going to pass through, like how really we are going to find out information about the voltage across and the current as well, the functions, and like by the end we will be able to relate them together in phasors. Now, the first component, it is when a resistor is connected with an AC source. The voltage and current amplitudes are actually related by the equation, which is Ohm's law, VR equals I times R. Okay, nothing is changing here because the resistance itself does not depend on the frequency of the AC source. Then whatever frequency we are going to have, VR is going to be I times R. Now, I will say here, we can graph the current and the voltage versus time for the resistor. You can see here that this is VR, okay? And I will say this is the maximum, the voltage amplitude here for the current. It is I, which is the current amplitude. VR, it is the instantaneous value at any time. It is IR times cosine omega t, which is the amplitude here, VR times cosine omega t. And for I, it is I times cosine omega t. One thing that is really important in here, we are going to understand that they are in phase. What does that mean in phase? That when we have a maximum here or a crest, is going to occur a crest. When we have here a dip or like the trough, this is going to be in a trough. Okay, then these here, the voltage and the current are in phase for a resistor, and we're going to see like how this is going to be different for capacitors and inductors. Now these are the phasors that I was talking to you about. This is a phasor diagram. This is really the current, and this is VR, the voltage. You can see here that of course their magnitudes, they're gonna depend on like what is the value of the resistor. I will say here, look at them, they have the same angle here, omega t. They are in phase, they rotate together. Then when this one is going to move here, this is going to move at the same value. This is the instantaneous voltage at any time, and this is the instantaneous current, which is the projection along the x-axis. And this is omega t, which is, I will say, the argument of the cosine. This is for the resistor. Now let's talk about the same thing for an inductor. Inductor, it's a coil. Remember, we were talking about that like the inductor is gonna resist the motion, is gonna resist the current to build up, because like the coils, they're gonna have an EMF that opposes that increase, and therefore there is gonna be a delay. And when we have an inductor connected with an AC source, the voltage and current amplitudes, they are really related by, like I will say, kind of similar equation, that it's always like voltage equals current times resistance. But the resistance here, we are not going to call it resistance, we are going to call it a reactance, and this is for the inductor, and therefore it's going to be inductive reactance. The inductive reactance, it is measured like this is here, it's a subscript, it's XL equals omega, which is the angular frequency, times L in henries. And the greater the inductance and the higher the frequency, the greater the inductive reactance. Then it has to do with L, but also it depends on the frequency, which is omega. It is 2 pi times the frequency. Now, when the resistor is replaced with a pure inductor, we know that I, it is I cosine omega t, and then there is an EMF that is gonna be like created, which is in the opposite direction, minus L di over dt. From the above figure, current through the conductor is from A to B, and it is increasing. Okay, I will say here, look at it. Okay, and the current through the conductor is from AB to B, it is increasing. Then there is an increase in the flux in the current, therefore di over dt is positive, and the induced EMF is directed to the left from B to A to oppose the increase in current. Then A is at a higher potential than point B. And finally, I will say the potential of point A with respect to point B is positive. Then VL is going to be plus L di over dt. And then we are going to get, this is the equation for the instantaneous voltage of the inductor. VL, it is negative I omega L times sine omega t. Now, the voltage VL across the inductor at any instant is proportional to the rate of change of the current, and the voltage and current are out of phase by a quarter cycle. Quarter cycle means 90 degrees. The voltage peaks occur a quarter cycle earlier than the current peaks. Then here we are going to say that the voltage leads, okay, with like 90 degrees. Okay, we know that cosine omega t plus 90 equals negative sine omega t. Therefore, we can say I times omega times L cosine omega t plus 90. This is VL. Then the voltage function with a head start of the 90 relative to the current. The current is going to be I equals I cosine omega t VL. The voltage at any instant is going to be I omega L cosine omega t plus 90. And we're going to see this in the phasors diagram very clear, and in the graph also. This is the graphs of current and voltage versus time. And here we have the I and V. Like if you look here, they are out of phase, and they are really, the voltage leads current curve by a quarter cycle. Okay, like the current is going to have its maximum here versus like the voltage curve is going to be starting here. Okay, look here, this is I cosine omega t, this is VL equals I omega L cosine omega t plus 90. Now, if we look at like the phasor is going to be clearer. Now here also I'm telling you that the amplitude, this is the uppercase L of the inductor, is equal to I omega L, and we define the inductive reactance XL is like omega times L, then VL, okay, is going to be I times XL, which is the inductive reactance. Here showing you, this is I and this is VL, okay, and voltage phasor leads current phasor by phi, which is pi over 2, or 90 degrees. Okay, this is omega t, and that is the 90 degrees between the two phasors. Okay, now it's the turn for a capacitor. In an AC circuit, we're gonna find that it is connected here to the source, and again VC is gonna be I times XC. XC, it is kind of resistance or impedance, or we call it capacitive reactance. XC, this is again, it is subscript xc equals 1 over omega c, and the greater the capacitance and the higher the frequency, the smaller the reactance. This is very important for you to understand when we analyze circuits with both components. Again, we're gonna have here the graphs of the current and voltage versus time. VC, the instantaneous voltage, it's going to be 1 over omega c cosine omega t minus 90. And for the current, it is I cosine omega t. The voltage curve now lags, okay, the current curve by a quarter cycle, or negative 90 degrees, or negative pi over 2. It's also very clear here from the phasor diagram, okay, that this is the current and this one here lags it's before by 90 degrees. Okay, these are really the phasors. Now resistance R is constant, omega L. XL is omega times L. This is the inductive reactance, and XC, it is 1 over omega C for the capacitive reactance. We have really this is the capacitor thing. I, it is I cosine omega t, and then VC across the capacitor, the potential of point A with respect the potential of point A with respect to point B here. This is VC, and then a Q, it is positive charge. Then the right hand side is going to be negative 9, negative Q. And then we know that the current equals at any moment dq over dt. Then it is I cosine omega t dq over dt. We can actually integrate to get a Q equals 1 over omega sine omega t, and then the charge equals the voltage at any moment times C. Therefore, Q equals C uppercase, which is the capacitance, times VC. And from that, we can say that VC at any moment, it is 1 over omega C cosine omega t minus 90. Now, comparing AC circuit elements, the graph shows how really the reactance or resistance with omega, or the angular frequency, the same thing, like it's going to be the frequency, because omega, it is 2 pi r, 2 pi f. Here for the resistor, see, it is independent of the frequency, then it's going to stay the same. For the reactance, we said is going to increase with frequency linearly, because it is XL equals omega times L. For the capacitor, it's the opposite. Therefore, if omega is 0 corresponding to a DC circuit, there is no current through a capacitor, because XC is going to go to infinity. In the limit, omega is going to go to infinity. The current through an inductor becomes small, okay, because the resistance is going very high. Here, this is application, the loudspeakers. I will say you can read, of course, more in your textbook, but in order to route signals of different frequencies to the speaker shown, the woofer and the tweeter connected in parallel across the amplifier output, and the capacitor in the tweeter branch blocks the low frequency. Also, we will have, like, I think one problem talking about this. Blocks the low frequency components of sound but passes the higher frequencies. And the inductor in the, like you can see it here in the woofer branch, blocks the high frequency component of sound that passes the lower frequency. This is very interesting. Okay, now here when we have the circuit is going to be all the components together, LRC circuit. LRC stands for inductor, resistor, and capacitor. they are all connected in series with an AC source. The voltage and current amplitudes are really related by V equals I, the current amplitude times the impedance of the circuit. The impedance of the circuit is not, you're gonna add R plus LC plus, R plus XC plus XL. We add them as vectors, as I will say, or as phasors. And the impedance of the circuit is going to be Z equals square root of R squared plus XL minus XC squared. I'm going to show you how really this was derived. Here, if you look, this is really the voltage, okay, and that is the voltage amplitude. This is VR. If you look, this is VL and this is VC. Like I can subtract them to get like VL minus VC, and then I'm gonna have these two vectors. They have 90 degrees between them. Then I can use Pythagorean, and therefore if I wish to add the voltage, V is going to be the square root, the same as the impedance relationship. It's the square root of VR squared plus VL minus VC all squared. But of course, we use it for the impedance here. This is the case when we have XL less than XC. The source voltage phasor lags the current phasor, and I will say when X is less than 0 and phi is negative angle between 0 and negative 90. This is here measuring the body fat by using bioelectric impedance analysis. These are like sensors or electrodes attached to the overweight patient chest are applying a small AC voltage that has a frequency of 50 kilohertz, and the instrumentation measures the amplitude and phase angle of the resulting current through the patient's body, and these depend on the relative amounts of water and fat along the path followed. And then they're going to provide sensitive measurements of what is really this body composed of. Now, power in a resistor, if the circuit element is a pure resistor, we know that the voltage and current are in phase, and therefore the instantaneous power, it is VI, which is always positive. Okay, this is for the resistor. For the inductor, if the circuit element is a pure inductor, okay, then the voltage leads, we said, by the current, which is 90, and the power is negative when V and I have opposite signs, and positive when they have the same sign. And the average power here is 0 because it is sometimes negative, sometimes positive. We will also, for the capacitor, the voltage lags by 90. The power is negative when V and I have opposite signs, and positive also when we have the same signs, and the average power is 0 again because it varies negative and positive. When I have a general AC circuit for any arbitrary combination of resistors and inductors, the average power is positive, and it equals 1/2 times the voltage amplitude times the current amplitude cosine phi, which is the phase angle. Here we have that equation. The factor cosine phi we called power factor of the circuit, and for a pure resistor the power factor is 1. Here, if you look, P average, it is 1/2 V, the voltage amplitude, the current amplitude cosine phi, which is phase angle of voltage with respect to current, and then we can have that VRMS, IRMS times cosine phi. Then both equations are really good to use. Okay, there is a case when we will have resonance in an AC circuit, and here we are showing the graphs for R and XL and XC and Z as a function of log omega. As the frequency increases, XL increases and XC decreases. Hence, there is always one frequency at which XL and XC are equal. And then XL minus XC is going to be 0. If you look here, they are intersecting at this point here, where this is, we call it the resonance frequency. At this frequency, the impedance Z has its smallest value equals simply to the resistor R, because they're going to cancel. And if you look here, if we look at the Z here curve, it has that minimum at this value when its value is going to be R, the resistor value only. Now, as we are changing the angular frequency of the source, this is really omega 0 will occur at when we're going to have omega equal 1 over the square root of LC. L, it is the inductance, and C, it is the capacitance of the circuit. Here we are showing you the graph of current amplitude as it is changing with the frequency omega for an LRC circuit. Of the voltage here, it is 100 volts, L is 2, and C equals 0.5, and we have 3 different values for the resistor. Okay, then this is for a high value, 2000, this is 500. Then the lower a circuit is resistance, the higher and sharper is the resonance peak in the current near the resonance angular frequency omega 0. Finally, transformers. A transformer is kind of a device that we are using to step up or to step down the voltage, and that is the purpose of a step up transformer is going to increase the voltage, and that is primarily controlled by having the ratio between the number of winding or turns, and in an ideal transformer, the ratio of the voltages across the primary and secondary is equal to the ratio number of turns in the coils. V2 over V1 equals N2 over N1, and these are representing the number of turns in the secondary and the primary coils. If N2 is greater than N1, then V2 is greater than V1, and we have a step-up transformer. Then I want to maybe upgrade from, I'm gonna go overseas. I have maybe my hair dryer. I want to operate it at, like I am now at 120. I want to make it to operate at 240 to 220. If N2 is less than N1, then V2 less than V1, and we have a step-down transformer like the transformers that we have for our laptops or for our devices that we are using. Okay, here I'm gonna stop because I have so many, like these are 20 pages of problem solving, and therefore I'm gonna have another video for that. Thank you.